Hello, welcome to the course SJ PHY2B02 Mechanics 2. The contents of this course is taken from An Introduction to Mechanics by Kleckner and Kolenko. In today's class, let's discuss about Module 3, Harmonic Oscillator. We are already familiar with the concept of a simple harmonic oscillator. In fact, we have discussed about it in the previous semester. So, as I say always, this is an important mathematical model in physics because many of the physical systems can be approximated to a simple harmonic oscillator or a harmonic oscillator in general. In particular, in last semester's course, we have seen that any bound system executing small oscillations can be modeled using a simple harmonic oscillator, because if you take the potential energy of a bound system, you can expand it in terms of a Taylor series, and if the oscillations are sufficiently small, you can neglect all the higher order terms. Then you are left with a quadratic function which corresponds to a parabolic shape. And we know that the simple harmonic oscillator has a parabolic potential function. So in that way, you can approximate a bound system using a simple harmonic oscillator model. So in today's class, what we are going to do is to derive the equation of motion of a simple harmonic oscillator and solve it. And we also get to know some of the common terminologies used to explain simple harmonic motion. Even though the concept is familiar, for the sake of completeness, let me start with the description of a simple harmonic oscillator, or what is meant by a simple harmonic motion. So consider a prototype oscillator, a spring mass system where mass m is attached to a spring of force constant K. So let x be the displacement from the equilibrium position. Now if you pull this towards the right and release it, you can notice that the system is going to execute oscillations about the mean position. Now if you monitor the oscillation, two things will be clear to you. First one, the restoring force is proportional to the displacement from the equilibrium position. Because when you pull it to the right and release it, the only force acting on the system is the restoring force. So here the entire oscillation is governed by the restoring force. Now if you pull it more towards the right, then it will be oscillating an equal amount towards the left. So more is the displacement, more will be the restoring force acting on it. So you can write F proportional to displacement x. Second thing, the direction of restoring force is opposite to the displacement. Right? So if you pull it towards the right, then the restoring force will be towards the left. As a result, it will be moving towards the left position. Once it reaches the extreme left end, then the restoring force now will be towards the right. Consequently, the block is going to move towards the right. So always the restoring force is opposite to the displacement. So I can write F is proportional to minus x. Now I can replace the proportionality with a constant k and write F is equal to minus kx. Now force is mass into acceleration. Since we are talking about one-dimensional motion along the x direction, acceleration is d square x by dt square. So my equation of motion becomes m into d square x by dt square equal to minus kx. Now I bring this term to the left hand side, m into d square x by dt square plus kx equal to 0. Divide the entire equation with m, d square x by dt square plus k by m into x equal to 0. Now I make an important substitution. Instead of k by m, I write omega naught square, where omega naught is square root of k by m. This is known as the natural frequency of simple harmonic motion. So with this substitution, I get the standard equation of simple harmonic motion, d square x by dt square plus omega naught square x equal to 0. So this is the equation of motion. Now I need to solve it. As you can note, this is a second order differential equation. So before getting into the details of solving this, let's discuss in general how to solve a second order differential equation. So I'm going to take a general equation a into d square x by dt square plus b into dx by dt plus c into x equal to 0. First step is to write the auxiliary equation, where instead of the second derivative I write the auxiliary term m square. Instead of the first derivative I write m, and the dependent variable here is replaced by value 1 and the quotient remains the same. So the auxiliary equation corresponding to this particular differential equation is a into m square plus b into m plus c equal to 0. This is a quadratic equation. Next step is to find the roots. We know the standard formula, m equal to minus b plus or minus square root of b square minus 4ac by 2a. Now depending on the value inside this square root, I can have different types of solution. Now the first condition, b square minus 4ac is greater than 0. So basically the square root is going to give me a real number, a real positive number. So I have two solutions, minus b plus square root of b square minus 4ac by 2a, I call it as m1. The second solution, minus b minus square root of b square minus 4ac by 2a, I call it as m2. So I have two real and distinct roots, m1 and m2, and the general solution is going to be x equal to a into e to the power m1t plus b into e to the power m2t, where a and b are constants whose value I need to find out. So as you can note, this is an exponential solution. The second condition, b square minus 4ac equal to 0. So consequently I am going to have only a single root m whose value is given by minus b by 2a. So in this case the general solution is x equal to e to the power mt a plus bx. So this is a combination of exponential function and a linear function. And if you note these two results, you can see that nowhere you are having an oscillatory behavior. When you have a harmonic oscillator, you expect the solution to behave in an oscillatory manner. But in these two cases, there is no oscillatory behavior. Oscillatory behavior comes in the third condition, b square minus 4ac less than 0. Now here what happens? The term inside the square bracket is a negative term, so you are going to get an imaginary number. Let's see how does that happen. So since b square minus 4ac is a negative number, I can write it as minus 1 into 4ac minus b square. Here 4ac minus b square is a positive number, right? Now I can take this minus 1 outside the square root, because square root of minus 1 is imaginary number I. So I can write it as minus b plus or minus I into square root of 4ac minus b squared by 2a. So I have two roots, m1 and m2, where m1 is minus b plus this term divided by 2a, and m2 is minus b minus this term by 2a. So I call it as alpha plus I beta and alpha minus I beta, where alpha is minus b by 2a and beta is square root of 4ac minus b squared by 2a. So once you define m1 and m2 in terms of alpha and beta, you can write the general solution as x equal to e to the power alpha t into a sin omega t plus b cos omega t. Sorry for the typo here, this should have been a sin beta t plus b cos beta t. Let me make the correction right. Okay, so the general solution is x equal to e to the power alpha t into a cos beta t plus b sin beta t. So you can see you have two sinusoidal functions here, which is going to give an oscillatory behavior, and the amplitude of the function is determined by this exponential factor. Since alpha is minus b by 2a, you have an exponentially decreasing function here, so you will find that the amplitude of the oscillation is going to decrease continuously. But on the other hand, if this factor alpha is 0, then you have only a sinusoidal function here, so you get an oscillatory behavior with constant amplitude. And you will see later that this is the basic difference between a simple harmonic oscillator and a damped harmonic oscillator. In the case of simple harmonic oscillator, this factor alpha is 0, so you have a constant amplitude oscillation. On the other hand, in the case of a damped harmonic oscillator, this has a finite value, so there you will find that the amplitude of the oscillation is decreasing as the time progresses. So this is the general idea about solving second order differential equations. Now we can go into the specific details of how to solve the simple harmonic oscillator equation at hand. So this is our equation of motion, d square x by dt square plus omega naught square x equal to 0. First step, write the auxiliary equation. So here coefficient a equal to 1, so 1 into m square plus the second term is absent, so I write it as 0 into m plus the third term omega naught square equal to 0. So a equal to 1, b equal to 0, c equal to omega naught square. So the roots are minus b is 0, so don't bother about that, plus or minus b square, which is 0, minus 4ac, which is 4 omega naught square, divided by 2a, which is 2. So we have plus or minus I omega naught, which I can write as alpha plus I beta. If you compare these two, you will get alpha equal to 0 and beta equal to omega naught. Now I know the general form of the solution, x equal to e to the power alpha t, some constant b sine beta t plus some constant c cos beta t. Now substitute for alpha and beta. Alpha is 0, so you have e to the power 0 into b sine omega naught t plus a cos omega naught t. E to the power 0 is 1, so you have the general solution of simple harmonic motion, x equal to b sine omega naught t plus c cos omega naught t. Alternatively, you can also write it as a cos omega naught t plus phi, where this extra factor phi is known as the phase constant, and when phi equal to 0, the solution is a cos omega naught t, and when phi equal to pi by 2, cos theta plus pi by 2 is sine theta, so x equal to a sine omega naught t. So in any case, you can note that the solution is a harmonic function. So you can look at the solution here, x as a function of time. Whether it is a sine function or a cosine function, you can see that x is varying sinusoidally as a function of time. Or the most general solution, as I noted here, is a linear combination of these two sinusoidal functions. Now you can arrive at this kind of a solution even without solving the equation explicitly. You can have a qualitative analysis. Why? Because look at our equation of motion, d square x by dt square equal to minus omega naught square x. Right? This is the equation of motion. Don't bother about this constant for now. So you can simplify this and write d square x by dt square equal to minus x. So basically, you want to find a function whose second derivative is the negative of the function itself. So you want to find f such that d square f by dt square equal to minus f, right? That's what you want to get. Now, what could be that kind of a function? One option is f of t sine t. Why? You take the first derivative df by dt, this is cos t. Take the second derivative d square f by dt square, this is minus sine t. So d square f by dt square is minus f. The second derivative of the function is the negative of function itself. So here one of the solution would be sine t. Another option is the solution being cos t. Why? Once again, first derivative is minus sine t, second derivative minus cos t. So once again, the condition d square f by dt square equal to minus f is satisfied. So either your actual solution could be either one of these, or the general solution is a linear combination of sine and cosine function. So I can write the most general form of the solution, f of t equal to a constant multiplied by sine t plus a constant multiplied by cos t. So here we did not consider the constant omega naught square. So if you put the constant omega naught square, then you find that the general solution is b sine omega naught t plus c cos omega naught t. So this is how qualitatively you can arrive at the solution. In any case, now you know that your solution is a harmonic function, which is a linear combination of sines and cosines, or you can write it as a single function by invoking the phase constant. Now, since I have two solutions, let me analyze the equivalence of these two solutions. Okay. We all are familiar with the trigonometric relation cos alpha plus beta equal to cos alpha cos beta minus sin alpha sin beta. So using this relation, now I can expand a cos omega naught t plus phi as a cos omega naught t cos phi minus a sin omega naught t sin phi, which is equal to the other solution b sin omega naught t plus c cos omega naught t. Right? Now, if this to be true all times, the coefficients of sin omega naught t and cos omega naught t must be separately equal. So let's equate the coefficients of the sine and cosine functions. First, the cosine function. Coefficient of cos omega naught t on right hand side is c, which is equal to coefficient of cos omega naught t on the left hand side, which is a cos phi. So the first equation is a cos phi equal to c. Similarly, when you compare the coefficients of sin omega naught t on either side, you get b equal to minus a sin phi, or a sin phi equal to minus b. So from this you can easily write the square on either side. So b square plus c square equal to a square into cos square phi plus sin square phi, but cos square phi plus sin square phi equal to 1. So b square plus c square equal to a square, or a equal to square root of b square plus c square. Similarly, when you divide the second equation with first equation, you get tan phi equal to minus b by c, or the phase constant phi equal to tan inverse minus b by c. So this is how you equate these two solutions. Now if you plot the solution x as a function of time, you are going to get a sinusoidal curve. Let's identify what are the important parameters associated with this solution. First one is x, which is the instantaneous displacement from the equilibrium position at a given time t. And what's a? A is nothing but amplitude of the motion, or this is the maximum displacement from the equilibrium position. Omega naught, as I said, is the natural frequency, which is also known as angular frequency of the motion. And angular frequency omega naught and linear frequency nu are related through the equation nu equal to omega naught divided by 2 pi. Phi, as I said, is the phase factor or phase angle. And there is another important parameter which is known as time period capital T. This is the time required to execute one complete cycle. So basically you start from this point, complete one cycle and arrive at the same point. So the time taken for one complete cycle is known as capital T, and this is inverse of the linear frequency, or in terms of angular frequency omega naught, I can write T equal to 2 pi by omega naught. And the corresponding length is known as the wavelength, time, the distance traveled in one complete cycle, that is the wavelength. Now the question is, once you arrive at the solution x equal to b sin omega naught t plus c cos omega naught t, if you know the angular frequency omega naught, can you exactly calculate the displacement at a given time t? The answer is no, right? Because you do not know the exact values of these two constants b and c. So you can find an exact solution only after you find the values of these two unknown constants. Now, how do you find the unknown constants? Since we are talking about a time-dependent equation, we can make use of the initial condition. So you specify at time t equal to 0, what is the position and what is the velocity. And using these two values, you can calculate the unknown constant. Because the initial position, initial velocity, these are experimentally measurable parameters, right? You can measure them physically. So once you get these two values, you can calculate B and C. How we do that? Let's see. So start with the general solution, S equal to B sin omega naught t plus C cos omega naught t. If this is the displacement, velocity is given by dx by dt or x dot. This is equal to derivative of sin omega naught t is omega naught cos omega naught t, and derivative of cos omega naught t is minus omega naught sin omega naught t. So this is the expression for velocity. Now let's calculate these two at time t equal to 0, because we already know at time t equal to 0 the position is x of 0 and velocity is v of 0. So at time t equal to 0, the left hand side is x of 0. This is equal to, when t equal to 0, I have sin 0 here, sin 0 equal to 0. Similarly, I have cos 0 here, cos 0 equal to 1. So on the right hand side, I have c. So the first equation becomes c equal to x of 0. Similarly, from the second equation, once again the sine term vanishes. So I have v of 0 or x dot of 0 equal to omega naught b, or b equal to x dot of 0 by omega naught. So I find the values of the unknown constants. Now substitute it in this equation. I get the exact solution, x of t equal to x dot of 0 divided by omega naught sin omega naught t plus x of 0 cos omega naught t, where x dot of 0 is the initial velocity, x of 0 is the initial displacement. These two are known parameters, and if you know the natural frequency or the angular frequency of oscillation, you can exactly calculate the value of x at a given time. So this is how you find the exact solution using the initial condition. Alternatively, if you consider the general form of the solution as x equal to a cos omega naught t plus phi, once again, if you want to find the specific value of the solution, you need to find the values of constant a and phase factor phi. Once again, make use of the initial condition. So here velocity v is given as dx by dt, which is minus omega naught a sin omega naught t plus omega naught t plus phi. So at time t equal to 0, x of 0 equal to a cos phi, and v of 0 or x dot of 0 equal to minus omega naught a sin phi. Now the second equation, if I take minus omega naught to the left hand side, I have a sin phi equal to v of 0 divided by minus omega naught. Now you take square on either side and add, you get a square equal to x of 0 square plus v of 0 divided by omega naught square, or a equal to square root of x of 0 square plus v of 0 divided by omega naught whole square. Similarly, when you divide these two equations, you get tan phi equal to v of 0 divided by minus omega naught by x of 0, or phi equal to tan inverse minus x dot 0 divided by omega naught into x of 0. So once again, the initial position x of 0 and initial velocity x dot of 0, these two are experimentally measurable. So if you know the angular frequency, you can calculate the values of the constant a and phi. Once you get the values of the constant, you can calculate the specific value of x at a given time. So this is how you solve the equation of motion of a simple harmonic oscillator using appropriate initial conditions. So that's for today. In the next class, we will discuss how to calculate the potential and kinetic energies of harmonic oscillators. Thank you.